Hello, myself Arunesh and my co-author Prateek Mishra are thankful to STC panel for providing us opportunity to present our paper in this forum. We both are technical leads associated with Arisent and currently working as technical consultants for a premium R&D client in Europe. In this presentation, we will be speaking to you about the techniques that can be used to test physical layer of narrowband Internet of Things. By Internet of Things, we are looking at a world where everything is connected to internet. It is expected to be around 75 billion devices to be connected to the internet by 2025. So to connect most devices, 3GPP has opted for low power wide access. Why? Because these many devices what we are talking about will mostly be very low powered and mainly in the low coverage area. So to help meet these requirements, NB-IOT has been developed as a non-backward compatible variant of EU TRAN, supporting a reduced set of functionalities to limit data rates and support high number of devices per cell. For this, several enhancements have been made, specifically in the PHY layer, those being coverage enhancements, coexistence with existing LTE GSM networks, and support for around 50,000 UAs per cell. Here in this presentation, we will be addressing the testing techniques that can be used to test these three major areas. So these are testing NB-IoT coverage enhancement, testing coexistence with existing LTE networks, and the capacity testing. Now, Prateek will give a quick introduction to NB-IoT file layer before proceeding to above addressed techniques. Over to Prateek.
Thanks, Arunesh. So, to start with, there are three operational modes supported in NB-IoT. The first one being standalone operational mode, which uses a 200 kHz channel from the GSM band, downlink and uplink separate. The second one being LTE guard band operational mode, which uses a single PRB from the LTE guard band, saying that it uses 12 subcarriers, 15 kHz each. The third being LTE in-band operational mode, which also uses one PRB but from the LTE bandwidth and also uses the same 12 subcarriers of 15 kHz each. Moving forward, a little more understanding of NB-IoT PHY layer. There are two types of narrowband carriers. First, the anchor carrier, which occupies all the mandatory signaling like BCH, sync signal, SIV1, and system informations. Secondly, the non-anchor carrier that can be used for shared channels for the UEs. This approach enables handling of multiple UEs in case of congestion. Then there are sync signals, the narrowband primary synchronization sequence, the narrowband secondary synchronization sequence. The functionality remains similar to LTE, though the location of these symbols have changed. The NPSS being scheduled on every 5th subframe and NSSS on 9th subframe of every other SFN. Now the target audience for NB-IoT are mostly low data rate devices, so the 3GPP stuck with only two transmission modes, SISO and TX diversity. So moving forward, there are only 5 physical channels in NB-IoT: narrowband physical broadcast channel, downlink shared channel, downlink control channel, uplink shared channel, and random access channel. In the uplink shared channel, it can be used for both data transmission as well as ACNAC. Now comes the most important aspect of the PHY layer enhancements in narrowband IoT: cross subframe scheduling, multi subframe, and channel repetitions. So the cross subframe scheduling and multi subframe ensure that the maximum 680 bits per transport block in DL and 1000 bits per transport block in UL are supported. And the channel repetitions help increase gain for devices in poor coverage. The more the channel repetition, the more probability of decoding reference symbols, as you can see in the picture shown in the slide. Now moving to our main area of focus here. Now, from all the previous explanations, we are aware of how important testing the physical layer will be before deploying commercially important as well as complex. So the challenges are, again, testing coverage enhancement functionalities, which include channel repetitions, multi subframe, and cross subframe scheduling. The second being testing coexistence with existing network like LTE or GSM depending on the operational mode. The third being testing capacity UEs, as we are aware that we are going to support around 50,000 devices per cell. Now, moving forward, Arunesh will describe the test bed, a generic test bed that can be used for testing NB-IoT 5. To you, Arunesh.
Thanks, Pratik. So now that we know what are the challenges in testing NB-IoT file layer, so we have a setup diagram that addresses a common way for testing NB-IoT eNodeB file layer. Here, automation framework will enable operation and maintenance entity to configure the device under test and all the simulators. The test outputs from the logging engine can be analyzed through the automation agents for various parameters like EVM, blur, throughputs, constellation, etc. etc. So this setup is practiced with few assumptions. First of all, the UE5 simulator we are using here is a NB-IoT compliant UE simulator. For example, we can use Aeroflex TM500. The second point is the higher layer simulator can generate MAC PDUs for file layer. And last one, signal analyzer and the signal generators that we are used here is licensed for NB-IoT. Now that we know the challenges and we know the setup diagram for testing NB-IoT file layer, we will concentrate on the testing techniques now. So first of all, as we said before, it is testing NB-IoT coverage enhancement. Testing NB-IoT coverage enhancement will require less number of UEs to load any specific functionality, and major focus area will be UEs that those are close to cell edge and far away from the cell center. With these functionalities, UE with the minimum coverage can experience higher signal to noise ratio with more number of channel repetitions configured for those UEs. So the key parameters to look into for this area will be mostly specification compliant. Few of them has been addressed in this slide, which is signal to noise ratio, error vector magnitude, channel bandwidth in uplink and downlink, modulation constellation plots for QPSK and BPSK, DLD codes by UE5 simulator, RSRP measurements, CRC pass and failures, location of transport blocks in frequency and time domain, downlink blur per UE in UE5 simulator. This, this setup required to test the coverage enhancement will require few assumptions as described in this slide. First of all, the fading simulator is introduced here so that we can reduce the signal strength. And secondly, the higher layer simulators should be capable of channel repetitions in file layer. So here we have an example scenario to test the coverage enhancement for NB-IoT. So we will configure one UE in LTE in-band operation mode. We can use any valid PRB index, 44 being described here. We are using LTE bandwidth of 20 megahertz. Assuming that all the signaling PBCH, PSS, NSS, SIB1s and system informations are present in fixed frame format. And there is no legacy UE present in the system so as to avoid any interference. So the test would be like configuring NB-IoT eNodeB5 with different channel repetitions varying across the simulation time. So the output result should be the simulator UE should experience increase in SINR with the increase in number of repetitions. So example numbers for repetitions corresponding to SINR is shown in this slide.
Thanks, Arunesh. So now we will address the testing technique for coexistence with existing networks for LTE and GSM. So testing the NB-IoT 5 with existing networks can be complicated when we consider only file layer as the software under test and all the other modules or layers are in simulated manner. Testing this area can be done in two methods. The first one being to combine the signals of LTE and NB-IOT and produce a frequency combined signal as described in the diagram, in the first diagram. Though this approach will not address interference issues for NB-IoT eNode B PHY, but can address UE behavior and in turn signaling impact caused in the uplink by the UEs. Now the second point, the second approach to combine the LTE and narrowband signals in the software itself or in the hardware RF controller in the setup. This can address the interference issues for narrowband IoT node UEs or the legacy UEs. Going forward, this is an example scenario for testing coexistence. We configure one UE, a narrowband UE. Operational mode, we can go with any, but here we have taken LTE in band, same cell ID. The PRB index, any valid PRB index, here we have considered 44. The LTE bandwidth, 20 MHz, assuming the NPBCH, SIV1 and SI are present in a fixed frame format. Number of legacy UEs, because here we have to configure a legacy UE. Number of legacy UEs, 1. PRB configured for legacy UE, 99. Excluding PRB index 44 because that has been reserved for narrowband IoT. Now the test is to configure UE simulator with one legacy UE and one narrowband UE for HARC or PDCP mode because we do not consider the higher layers here. Activate both the UEs to perform cell search. Load the PHY with maximum possible downlink transmissions. Configure the UE simulator to transmit uplink for LTE and narrowband UEs both. The result expected should be both the UEs be able to decode MIB, SIV1 and system information and no blur is observed on legacy or narrowband UE. Now moving forward, the third technique, that is to test the capacity UE. Now testing capacity UE will ensure the stability and robustness of the PHY layer for maximum load. Though in field or real-time scenario, the eNode B or modem is not expected to be loaded all the UEs at all times given the scheduling procedures in narrowband IoT, for example cross-frame scheduling, or there are few clauses in the 3GPP specifications. Testing capacity UEs will require extra long durations and testing of several possible configurations. Though as the testbed will be having simulated entities, some plausible limitations are expected, such as simulation length in the time domain. As the scheduling will require scenarios spreading across multiple hyper SFNs, there can be a limitation in simulators. Logs capture length, as mentioned above, the same limitation can be applicable to logging engines used. The key KPIs that need to be analyzed when testing PHY for capacity UEs can be the block error rate average for the whole system or the cell, the block error rate per UE, the average throughput per cell, average throughput per UE, any alarms generated, memory utilization of the device under test, CPU utilization, and also testing capacity UE will require a narrowband IoT capable UE simulator, for example, Aeroflex TM500. It can be configured with the same cell ID and frequency to achieve capacity UEs. Now going forward to the example scenario for testing capacity UE, here we have configured around 50,000 UEs. We can go for 50,000. The operational mode we have used here is standalone. We can go for LTE in-band or guard band as well. The same assumption applies that NPBCH, SIV1, SI are present in fixed frame format so that we can decode bit by bit, and no legacy UE are present. The test is to schedule the NB UEs in downlink without any repetition so that we don't use a lengthier simulation as shown in the diagram. Now the result expected will be no assert is observed, no blur is observed, memory and CPU utilization is under threshold boundary. With this, we can conclude the presentation that the narrowband Internet of Things observes a major and complex change in physical layer implementation A wider as well as in-depth testing of file layer for NB-IoT plays a crucial role before product is commercially rolled out. The above mentioned techniques that we have discussed previously will ensure all the basic NB-IoT physical layer functionalities are tested and overcome the challenges described. With this, we end our presentation here. Thank you very much.